Hey guys, not entirely sure how this works, but I hope it's working. So we are going to be working on the circuits mini lab. So if you have your fat packet, please take that out. If you have any questions during the process, please write in the live chat, and I'll let you guys know. I'll try to answer them as quickly as possible. So please make sure you want to look at the first challenge. And the first challenge is you have a light bulb and a battery. And it says a piece of wire, but I know most of you probably don't have a piece of wire. If you do, feel free to use it, but you don't need it. And so right now, if you look at the first challenge, I'm going to open up my page and actually read it. If you look at the first challenge, it says challenge one, light bulb basics, using only one light bulb, one battery, and one piece of wire. These. So if you don't know, these are the official way that we draw. This is what a light bulb looks like. A wire is just a line, and this large line and the smaller line connected is what a battery looks like when you do the drawings. You don't have to do that right now. We'll work on it. But what you want to do right now is sketch two configurations that did not work to light up your battery and two configurations that did work to light up your battery. So take a second to try that right now. So play around with your battery. I'm going to be awkwardly still streaming and playing with a wire and battery. So again, hopefully I see a couple people joining us here. 15. Oh, not bad. So take your light bulb and your battery. You don't have to use a 9 volt. I tried using a 1.5, but mine are all dead. Because if you use a 1.5, it should look a little brighter than this does, and you can even barely see this. Yeah, Unseen, you did. And if anyone remembers Aiden Fideli, graduated last year. He almost, well, I guess he saved it. But if you leave these attached, or more correctly, if you do direct like this, you'll notice the wire gets hot very quickly. And if you leave it, you'll actually burn it out, possibly causing smoke and a fire if there's anything close that'll burn. So don't do that. I highly recommend not to leave these on your 9 volt batteries when you're not using them. I would take them off. Hopefully, you've started playing with it and have some idea of what does and does not work for this. So, what does work, and again, hopefully you've taken the chance to try it. If you connect two to one side, that's not going to work. And even if you connect both to one side, you'll notice they get hot again. You have to do one on each side. And since these are not LEDs, LEDs are one directional, these are incandescent, so it will work either direction. And so I'm going to draw that on the board and follow proper safety procedure and disconnect at least one of these terminals. So what that looks like is for anything that does not work is anything that does not complete the connection in one way or form. Or, I'm not liking the way orange showing up. I'll try purple. Or if you connect one-sidedly to things, it has to be a complete connection. And so what does work is either way we have direction. This doesn't matter if you have more or less wire. Even if you add additional wiring, it's still going to work. And again, these lines signify that it's a battery. These lines signify that it's a light bulb. These little curly lines. And these straight lines are just wires. So that's the basics. Challenge 2 is, I'm actually going to probably go off screen. Maybe I'll grab my dog, just because I'm bored. No, no, you don't. I did use a 9-volt battery. You can use a standard 1.5 volt. The 9 volts will work as well. It you just might burn out your light bulbs accidentally. Like if you hear a little pop, but then it doesn't work anymore, you blew out the little filament inside of it. Um, but my 1.5s, normally it should light up much better than this. My 1.5s are definitely dead, so I would need to buy more. And so if you have the 9 volts or if you have a 1.5, anything would work. I am going with my 9 volt because I don't have anything else. And this one's already partially dead, so it's fine. It's not giving me a whole lot of power. Um, so no, Navi, we're not using resistors yet. Just use your light bulbs. Tomorrow I'll have another video either live if this works for you guys, or I'll pre-make one, hopefully better. So right now we're only using these light bulbs. Is that the one from class? Yes, yes it is. So it's the one that I used last year that still has a little bit of juice. I'm gonna have to go buy one for actually doing the resistor labs for them to be accurate. So hopefully Safeway has them. We're in sort of a weird time, but it should be fine. I don't think anyone's going out and buying 9-volt batteries. It's not really a hot top item right now. Anyway, so challenge 2 is we're now looking at what happens with the different ways you can connect these. And so you can again set up, please do this, or at least if you aren't doing it with me, do it at some point at home, try it, play around with it. How can you connect these so that they're either bright and or dim, and what do those connections look like? Um, so I'm going to step away so that you try it. Otherwise, I feel like you'll just wait for me. So go ahead, try. How can we set these up so that they're either bright and or dim? I'll come back in 2 minutes. I might go grab my rat just so she has some playtime. But go ahead, do that. I'm literally going to step away now. Try it. Aye. Do you want to see the rat? Because I can put it on screen, but I know some people are actually afraid of rats, so I don't always want to bring her on screen. Um, Actually, no, you're gonna burn your fingers if you short the circuit. So if you feel it getting hot, you've connected them wrong. Don't connect them that way. So this is my rat. She's currently a lone rat. Her name is Zora, after Zora Neale Hurston, a famous African American author from, I believe, the 40s. So yeah, she's really sweet. Hi. I woke her up, so she's a little grumpy. Um, yeah, she's a little fat. She has upper respiratory problems, so we like to keep her a little fat just in case she ever stops eating. When rats don't smell well because their nose is stuffed, they stop eating because they're just not interested. Do a flip. She'll do spins, but again, she's sleepy and I don't have any treats for her, so I don't think she's gonna really be interested. Anyway, so hopefully you guys did take a chance to try it. You're not going to burn your fingers. If you connect them to the same place, i.e., this is what if anyone's like, oh, you're going to short a circuit, this is what shorting a circuit is, when you connect them directly and don't provide any resistance in between. So there are 2 main ways that you can do this. And I like to say you're either making them hold one hand or 2 hands. So if we make them hold one hand, the easiest way to do this is put them. Yes, Navi, it is. Come on, let them figure it out. So you're gonna have them hold one hand, and the easiest way to do this is twist them together. And then you can connect each side. I don't like to twist these just because they get beaten up really quickly. And unless you have wire cutters at home, you can't really fix it. And so if you have them hold both hands, you'll notice they both show up and they're kind of bright, but not particularly. Whereas if I put them together and have them hold both hands, I'm going to twist these in so I don't have to hold it, and hold both hands, they are now going to be much brighter than they were before. Oh, good. That showed up pretty well on camera. So they are much brighter than they do before. No, rats just like us are not good conductors. Um, she might try to chew it though. I've had a rat chew through an electric cord, which thankfully wasn't plugged in. So as far as what challenge 2 looks like in circuit drawings would be for them to be dim. How's green showing up? Okay. For it to be dim, they're in the same line. So they're connect one hand, but one hand each touches the battery. These actually show up dim, even though it looks like they're more directly connected. But that's because the parallel ones, when they're holding hands, see they're holding two hands here instead of just one hand, this is going to be bright. And this isn't necessarily a hard and fast rule. This is just if you're working with two particular ones. So this is going to be dim, this is going to be bright, and we're going to talk about why in a second, essentially how electricity and electrons move through a circuit. And sorry, I lost my train of thought. And so we're just going to go over that. So the next challenge, or continuing challenge 2, was using that third one. And I'm kind of curious, there's normally 2 ways to do this. One follows along with this rule, and one seems completely opposite. And we'll break that down in a second. And so I'm going to do one of them that follows the rule. And so I'm going to do one set of parallel. So I'm going to do these 2 in parallel with each other. Excuse me, series. These 2 in series with each other. And this one in parallel. And so they're all holding hands, but the way I'm going to attach this to the battery is going to maybe look a little different and sometimes hard to see, which is why I do want you guys to play with it. Hey, hello, Eduardo, how's it going? So I'm going to hold one side by itself in parallel and the other 2 in series. And the interesting thing, it's a little hard to tell for you guys, but this one is actually brighter than it was before by just a little bit, which is sort of interesting. It's a little hard to tell the incandescence a little more if you actually use the multimeter and the resistors, but this one's actually a little bit brighter. And so this is one way we can get one bright and 2 dim. And so that would look like, again, orange does not show up well. So if we wanted to do one bright, 2 dim, it would look something like this, where we have one all by itself in parallel. And so we call this parallel because literally these lines are parallel to each other in the way that we draw them. Not physically, but circuit-wise they are. And these are we call these series because it's one after another. And so this is where they hold one hand and one hand goes somewhere else. Parallel is both hands are being held per light bulb. So we can see this light bulb, one hand goes to this light bulb, one hand is actually going to connect back to the battery, and same for this one. And this one, both are held. So what we do here, well, actually, let's try that last one that I said that maybe seems contradictory. So this is what we would expect, where these two are dim in series, just like we thought, and this one is bright because it's in parallel, just like we did before. One that seems a little counterintuitive, however, is if I set it up differently. So I can put my two parallel, and then that last one in series. And so if you guys haven't done this, quick prediction, which one's actually going to be the brightest? Although I feel like I may have hinted it. So I'll ask. I actually help him edit his videos, but you can actually see me credit on one of the conductor's ones. I just caught a spelling mistake, which is odd for me. The last one, let me show it to you physically first, is these two are in fact extremely dim, and this one in series is bright, which is odd even though these are parallel, which is weird. And so I'm going to draw that up on the board, and maybe then we'll kind of get into conclusions and electricity basics, and I'm going to erase some things. So the way we would draw this one is we have two in series. Excuse me, that didn't look right. No, it looks better like this. So we have the two in parallel first, and then this one in series. Strangely, the ones in parallel are dim, but the one in series is bright. And these actually are like our two main laws that we're going to work on, which is Kirchhoff's junction rule and loop rule. Before we get into that, we'll actually talk about what's going on here. So hopefully some of you guys know a little bit about electricity. It's the only unit we won't probably actually get to cover in class. We'll see what actually happens with class. No one knows yet. But what's happening, and hopefully this is okay, I'm going to erase this. This is YouTube, so you can just rewind it if you really need to. But what's happening in our circuit is we have our battery, and hopefully you know how batteries work. If you were in Gulshan's class, you definitely should. If you weren't, basically we have a positive and a negative terminal, and convention says that, I'm going to tilt this so it gets a little more this way. Convention says that the positive travels, and if you know anything about atoms and electrons, that's convention. That was just Ben Franklin had a 50-50 chance and he picked wrong. It drives me crazy, but that's convention, yeah. So we say the positive charge travels in the positive direction around the circuit. So, and I think Flipping Physics got into this a little bit on one of his videos that I sent out for this week, I believe. And so the positive charge moves through this. And so when it leaves home, it has a little bit of potential energy in it. We call that electric potential, electromotive force. The unofficial name is voltage. And so that's why this 9-volt battery by default has more juice in it than this little 1.5. And it's actually because their stuff's different. All right, she's getting antsy, so I'm going to let her go home. And in case any of you are wondering why I went to 2 different places to get her, she has 3 different cages because she's spoiled. So the proton is said to move here. Obviously, we know it actually is the electron. So we say the electron moves in the negative direction around the circuit, and this is the positive. Yes, it's physically the electron moving, but we always say the positive charge moves because no one decided to fix it, and that's just how we do it now. So this little charge, and let's say with 9 volts, it has 9 volts when it leaves home. And obviously a circuit is a continuous flow of electricity. If you get a interrupted flow, that's when your lights flicker and things turn off. So this is a continuous flow of electricity or charge. Each individual charge gets 9 volts. And so the definition of voltage is the potential energy per charge. So each little charged particle gets to carry a little bit of energy with it. And so when it makes its way through the circuit, by the time it's done, it goes home with 0 volts. So every time it passes through a resistor or a light bulb, it loses energy or uses energy up. So for example, light energy, that electric energy gets turned to light energy or heat for incandescent, but does not necessarily do that for LEDs. LEDs do a very good job of transferring just to light energy, not to heat. Resistors just do heat, no light. Main thing, energy is dissipated. And so the important thing is that at every light bulb, it loses a certain amount of energy. If there's only one, it loses all of its energy there. And that's why it's bright. If, for example, we have things in series, let me draw that nicer. And if I start with 9 volts and I have my little 9-volt charge traveling around here, it's so weird doing a positive charge. I have my little 9-volt charge running around here. How much is it going to spend if those are the same light bulb? Quickly type in your answers. How much voltage? Yeah, it is. Also in the homework videos, but I did want to go over it additionally. I'll do the dog later at the end, so stick around to the end and I'll show both my dogs. I have 2. One's pretty new. So what I want you to do is, if this one uses up 9 volts, the whole 9 volts are used on one. If I have 2 light bulbs, how much volts go to each one of them? So for each light bulb, how much voltage gets used on each one, or how much we can think of as energy? Some of you guys have started in the comments. And so yeah, some of you guessed accurately, some of you not, but that's fine. We're just starting out. It's going to be 4.5. Because if I lose 4.5 here and 4.5 here, we're going to have 0 by the time it goes home. So basically your charges do not go home until they're completely out. If it's equal resistance, they spend equally and it gets split in half. If they are not equal, it will get split unequally, but will still add up to 9 volts total, or however much your starting voltage was to end with 0 volts. So, and that's sort of the kind of basics of this. And so the reason why these are dimmer is because they have less voltage. Whereas if they are in parallel, can the same little charge go to both of them? So if I have one charge, does that charge hit both of them? What do you guys think? Yeah, it will be 9 volts actually. So, but does this little charge go to both places or only hit one spot? Less current, but kind of knobby, kind of. That's not actually always entirely true. So, but yeah, so it does not go to one. So what happens is, because remember, this is a continuous charge, I'm just drawing one because it's easier, but they split up. And this is a different rule. So I'm trying to draw them more numerous on the shared path, less numerous on the split path. But basically, you can think of your wire as a one-way road. Your electrons do not go backwards, they can only go forwards. So if they have two roads to go on, you'll have some go this way with their 9 volts, and then some will go this way with their 9 volts. Either way, since this is the only thing they're hitting before they go back home, 9 volts are going to be spent in both places. And then they go home with 0 energy. They're done for the day. They retire. And so this is why your parallel ones were brighter than your series ones, because they got more voltage. Navi, they each get less current than if there was one, but not necessarily less current than in a series. They actually get more current when they're in parallel, which we'll talk about law of resistance. You want to retire, don't we all? But it's not happening. So they each get 9 volts, which sort of begs the question, what happens when we put the 3 up? Like, what was going on there? So, again, if you have any questions, I'm going to erase this, so please post questions in the comments. If you keep typing too much, just say, hey, you guys, just make sure if I miss a question, if you guys could try to bump it, because I can't read these the whole time. All right, so any good questions? No. No, okay, cool. So as for our other circuits where we had 3, one was that they were in parallel with 1 in series. And then the other one was that they were in series with 1 in parallel. All right, really quickly try to see if you can identify which of these are going to be bright. Each one has 2 dim, 1 bright. So try to identify for yourself quickly which one is going to be bright, which ones are going to be dim in each one of these circuits. Have we thought about it? Yes, no, maybe, kind of. So which ones are going to be bright? Which ones are going to be dim? What are we doing again? The circuits packet, the new one, the big new fat packet with the lab on front, Giuseppe, that one. All right, so let's choose a different color. So here, this is going to be our bright one. And here, this is going to be our bright one. The other 2 for each one are going to be dim, which I should have numbered them looking back. And so for this one, number 1 is going to be bright, and for this one, number 3 is going to be bright, even though they're in very different positions. This one's in series, and this one's in parallel. And it has to do with our 2 main laws. And so the idea is that for this one, it has a voltage split, but a current. Basically, how many volts does this first one get compared to this one? So again, let's just say, imagine we have a 9-volt battery. How many volts does 3 get? How many volts does 1 get? Go ahead, please type in the comments what you guys think. So how many volts do each one of these resistors get? I'll try to redo it, Jocelyn. And yeah, Jan, you are right. So number 1 gets only 4.5 because our electron started with 9 volts. Our electron, I mean our positive electron, started with 9 volts, and but it still has to save some so that it can get all the way home. So it has to pay equal amounts because these are all the same light bulb. If any of yours are naturally just brighter than the other, they might actually not be the same light bulb. Production's not perfect. So each one of these light bulbs should have the same amount of resistance, should take the same amount of voltage depending on if that electron actually goes through it. And so what happens is your electron does not lose all of its energy here, it only loses some of it. And so by the time it's done, it started out a 9-volt electron, but now it's only a 4.5-volt electron, and then half go this way, half go this way. And then they both spend 4.5 volts here so that they can have 0 volts by the time they get home. In this case, however, your electron, your little 9-volt electron, can either go on the path where there are 2 light bulbs or 2 toll booths, you can think of it this way, or it can choose the path with only 1 toll booth. Which would you pick? Probably the one with only 1 toll booth. It's more expensive, however, but you don't have to stop as much. You go faster. So you have quite a few going this way. And so they can go this way and then go all the way home without hitting another stoplight toll booth and get to use all their energy here. So you're going to use 9 volts. So what about my 1 and 2 and my 2 and 3 here? So this one also has 4.5. And so these actually have the exact same voltage, but are still different brightnesses. Yeah, thanks, Jocelyn. It is the front page. Yeah, but this is a lab. Of course, it takes longer. Can you go to the? Yeah. I mean, theoretically, you could take this with you to the bathroom. No one will know. Yep, you're right, Giuseppe. So do I, but we don't have to tell our secrets. So all 3 of these, sorry for this side, have 4.5 volts. But this is the bright one. Whereas for these 2, 1 and, oops, no one caught that? So 3 is the bright one. It has more volts, so that makes sense. It has more energy. But 1 and 2, how many volts do they each take? Go ahead, type. How many volts do each one of them take? You're on a computer, then you're right, you can't, but run quick, I don't know. So they're each going to take 4.5. Because it's whatever electron goes down this path starts with 9 volts, but it has to go through essentially 2 stoplights in our little electric road. And so each one is going to take energy, and they're both the same stoplight, so they're going to take the same energy. By the time he gets home, he's going to be exhausted. So each one is going to take an equal amount of voltage so that it adds up to the total original energy of 9 volts. So why the heck is this one bright when it still only has 4.5 volts? And that's because the voltage doesn't exactly have to do, as this live going to be saved theoretically. I really haven't done this that much, but it seems to save, so it should work. You would be surprised how many misspellings of my names you can get. But, so why is this one bright? And so that's because brightness is a measure not of the voltage. Brightness is a measure of the power. So, like if you ever go to the hardware store, which hardware stores are still open, so you can go to Home Depot for whatever reason. So the power is like if you go and you see, oh, it's a 60-watt bulb or a 100-watt bulb, and if you guys actually did the power work for energy, you'll notice the units are exactly the same. And so power is dependent not only on voltage, but on to current. So there's a couple ways we write this. I wrote it backwards of the way I normally do, but basically power, which hopefully you guys remember is a capital P, is voltage, which for simplicity is actually just a V, and for non-simplicity, current is an I. Standardly, I see it like this: P equals I V. And so this one's bright not because it has more voltage, but because it has more current. And so current is exactly what it sounds like. It's the flow of electrons. Eduardo, I actually think they might, although probably right now the answer is no. I would wait till they restock. So this one has more current. So voltage is how much power it starts with originally, and that depends on that individual electron. The current is the flow through it. So each one of these has a split flow. This one gets all of the current, which if we give a number to some of these resistors, we could solve, but I'm not going to do that right now. And so I'm just going to say for the current, it gets all of it. So all of the current, because you can't be an electron in this circuit and not go through number one. It's like that one-way road. There's only one way to get into the parking lot, and you have to go that way, and you're just going to have to be stuck in traffic. Whereas later, it splits into two roads, and so now your electrons have different paths that they can take. And so because they're equal, they're each going to get half the current, or half of your initial current. So they're each going to take half. Later, all right, your current splits up and you come back together and you have a entire loop done. This one, they all, well, not exactly. They all get part of the current. I'm going to say this kind of odd. So who's going to get more of the current? 1 and 2? Because 1 and 2 have to get the same current because it's the same road. You can't have more cars on the road and end with less, or vice versa. Whatever you started with at the beginning of this road, you're going to end with. We don't make people disappear. We don't make electrons disappear. Which path is going to have more current, 1 and 2, or 3 by itself? Giuseppe, I really would like you to do it. I can't make you, I can't really check, but so yeah, Eduardo, 1 and 2 will definitely have the same. Which one will take more current? And so the way to think about which one's going to have more current is, would you rather drive on a road with 1 stoplight or 2 stoplights? Think about it. If you actually drive. If not, you don't care. You're just in the car on your phone anyway. So would you rather, for speed's sake, to get through a light faster, would you rather go with 1 stoplight or 2 stoplights? And your electrons want to avoid the stoplights. Their entire goal is they start here with a lot of energy, and their entire goal is they're driven to get home by the electromotive force. So yeah, Simon, that's just not going to work out well. But so this one is going to have, oh gosh, let me calculate. It's been a while since I've had calculate. Doing some math, and if you follow along, great, and if you don't, I'm really sorry. I just want to make sure I do this correctly. Three, right, yeah. Okay. All right, and so this one is going to have 2 times the current of 1 and 2, whereas these are going to have the same current. So this one's going to have twice as much current because it's half the difficulty to get to. So you're going to have way more current on 3 than you're going to have in 1 and 2 because it's a much more difficult road. Your electrons would prefer to take the easy path. Flows like water, you're always going to be taking the easier path. So you're going to have more current through 3. And so that's another reason why this one is absolutely brighter. It both gets more voltage, but it's actually also going to get a larger proportion of the current. Not a single one of these gets the total current, however, is whatever current we started with here is going to have to get split up because you can't have an electron here is not going to hit every single light bulb or every single resistor. So this one gets all the current, and here nobody gets all the current. They all get a proportion. And so that's why we get these 2 different rules. And so that leads us to 2 big rules. I'm going to erase again. While I'm erasing, please think of any questions, things that you want clarified so I can go over them. So the road takes longer even though it is just by 1 stoplight. So they're always going to go for the path of least resistance. So it's just like your water. Water does not flow uphill. Electrons do not flow backwards. It's always going to go the path of least resistance. And so what that tends to look like is they'll take the path with the least resistors. A light bulb is just a fancy resistor that also lights up. And those tiny little things I gave you with the wires attached are just resistors. Yeah, it is like traffic. You just want to avoid the traffic. So we have 2 main rules. And one is called the Junction Rule. And the other is standardly called the Loop Rule. These are both part of Kirchhoff's laws. So the Junction Rule and the Loop Rule. So the Loop Rule says that in every loop, all voltage is consumed or used. And so what that says is no matter how many loops you have, and I'll define a loop here. Literally a loop is if I can do a circle to my battery and back. I'm not sure if we can see that. So I have 2, 3, I have 4 loops here. Every single loop gets 9 volts, or however much battery or however much voltage this battery is. So this one gets 9 volts, this one gets 9 volts, this one gets 9 volts, and each one of these gets 4.5 volts because the whole loop gets 9, so there's 2 of them, so they have to split it. And so that's the loop rule. And so it's the idea that energy is conserved. So this is a rule of energy conservation. Is that however much energy you start with, you're going to use through that because energy is conserved. Basically, your electron is not done until it gets home, and it can't go back home if it still has energy because it's going to go hang out with all the other electrons, and they do not hang out when they're all energetic. So this is an energy conservation rule. So this is for voltage. The junction rule is for the current. So the junction rule says that the amount of current into a junction is equal to the amount out of a junction. And so what that looks like is every time we have one of these junctions, i.e. a place where the circuit splits, this would be a junction. Should I draw that bigger? Yes or no? Especially for people watching on their phones, it might look small. Sure, lovely, you can take these as notes, or you can, it's a lecture note, I don't know. We're gonna figure this out. So no one stated that they really want, you want it bigger? Yes, no, okay. So I'll make it a little bigger. I imagine if you're on your phone, this is very small. Hopefully that is big enough. So if I name this, let's just call this one A and this one B, and this is my total because it's my entire circuit, is whatever, getting different colors here, is whatever current comes in. So if I have some amount of current, remember I stands for current, later when these split, I have some amount of current that's going through B and some amount of current that is going through A. Even though I have current that is going different ways, the total current, A plus B, should be equal to whatever total current you started with. And this is an extension of a conservation of charge. So conservation of charge is just like the conservation of mass. You can't have more mass than you started with unless you change your system or there's something else there. And so charge is the same way. We can't suddenly have more or less electrons than we had before. So I'll just write that, conservation of charge. And so basically, anytime we have electricity, and this is the same thing that's going through your walls, just on a much grander scale. And so this is your junction rule and your loop rule. I saw a question, Is there an equation that connects energy and circuit? Yeah, there absolutely is. One is just voltage is essentially equal to the change in energy over the charge, i.e., where we talked about back then, the amount of work done per charge. So that's how much work each little electron can do. Obviously, that doesn't tell us about the entire circuit. So work is how much energy is done, or you're gonna have to rewrite the whole question, Navi. So it's how much work is done. Current, and so that's why if we combine them, remember power equals work over time. Current is the amount of charges per time. So that's like if you watched a freeway, you could count how many cars go by per second. We could watch how many charges go by per second, except it wouldn't be by per second. It'd probably be by microseconds because they go extremely fast. That's not a G, it's a Q, which is why it probably looks weird. Oh, yeah. We're getting there, Navi. So this is the amount of charge per time. And so Q equals charge, T equals time, which is why if I do voltage times current, we get work per charge times charge per time, which gives us work over time, which is our original definition of power. And that's why they're actually the same thing. And so that's why we say you can use a lot of power running up the stairs, mechanical energy, or you can use a lot of power. I'm doing 3 lights because this is actually a very dark room. I'm using a lot of power just to get some good lighting in here. And both are power, both are energy over time, and it's just the different types of energies that are being converted. And so actually there was a really good FRQ problem last year on converting mechanical energy, power, using electrical energy. And it's the same thing. This power is the exact same as the other power. It's still work over time. It's just because we don't use work and time by themselves in circuits, we do V times I. All right, and then the very last thing I'm going to go over, which is definitely in your notes, and we'll be practicing tomorrow. So tomorrow's the day, since Amazon extremely delayed, I still don't have my resistor, so theoretically my resistor should arrive today. Otherwise, we'll just do a sad hashed version. But tomorrow we're going to do in living practice Ohm's law. All right, I'm going to erase all this again. If you want to take notes, you can just go back. And so the really big equation is voltage equals current times resistance. That's a terrible one. Better one. Voltage equals current times resistance, V equals IR. And so the idea is that if you have more resistance, aka more resistors, more light bulbs, your electrons are a lot less likely to leave home. If it's really bad traffic conditions, you're just going to wait because it's going to be a long waiting time, so your current goes down. These are, remember, inversely proportional. However, the faster or the more resistance something has, the more voltage it's going to take to get through it. So the worse traffic is, the more energy it's going to take to get yourself through it. So those are directly proportional. Same thing, current, the faster you're going through it, the more energy you're using to do that, because there's more energy per time going through that little piece. So, and we're losing focus, so I'm going to cut this short very soon. And so that's the basic idea. And so tomorrow we're going to start setting up circuits and trying to get intuitive understanding, and then I'll teach you the calculations. Because if you only rely on calculations, as you might understand again after seeing the FRQs, there's very few calculation parts of it. Yeah, they want to check you can calculate, but most of it's going to be very conceptual. They're more likely to give you a complex circuit and say, which one's bright? Which one has more current? What would happen if we short-circuited this part? And so I want you to have a very good intuitive understanding about how this works in a real circuit. And so tomorrow we're going to learn how to use some multimeters. If any of you are borrowing your parents, I highly suggest you get them to look at which one. Main thing is when you're doing it, we want to make sure when we're measuring voltage, we're actually on the voltage side, signified by a V. Yes, I'll show the dog. Can we combine circuits with force and kinematics? I haven't seen that very often. It best combines with energy. Sometimes I'll do it with some electricity equations. Electricity by itself, circuits, so not circuits, but static electricity, comprises maybe 1 to 2% of the entire test, which is why we're not really focusing on it. But I haven't really seen forces and kinematics. The only place they could maybe mix it in is if you do energy to force, but you'd have to convert through energy first. I don't really expect that, but then again, they're very good at thinking up problems. But at what time? Great question. Probably if this time works well for people, I'll just do same time, same place. Missed this one because I was sleeping. Then maybe comment at the very end on like preferred times. I'll obviously pick one that works for me. Um, how will we review? God only knows. We don't know. There are thoughts that school may not start again, so we will definitely see what happens. Um, I'm actually probably gonna get quizzes, and I'm not gonna grade them hard, but I just need to figure out like where we're at and how much we can actually. Then you know what? Good for you. Um, but actually, if you're in California, Gavin Newsom said he doesn't think any of them are gonna start, which is the governor. If you don't know that. So yeah, we don't know. We don't know. And then as far as Navi was saying about the triangle, this is the I don't understand algebra. Like, is there your practice booklet? Yeah, I'm actually gonna be sending out copies for it. It's 5 Steps to a Five, written by Greg Jacobs. Any additions, great. Uh, I've actually been using it throughout class, and Greg Jacobs is the person I also steal labs from, as well as a lot of your problem sets. He's very good. He has pretty much an 100% pass rate. He teaches at a fancy prep school, so you know, but he also teaches it to some freshmen. So he's very good at his job. I'll be sending out, I'm going to start probably scanning with my phone today and we'll see how they turn out. And then I can also send out a link if I can find any cheap ones on Amazon. Amazon is delaying a lot of things because of their high workload right now. So again, we'll just kind of see how this situation evolves. But anyway, this is V equals IR written out as a triangle. And basically this is, if it's these two, you multiply to get the third. So if you cover up one, this is going to be division, this is going to be division, this is going to be multiplication. So it's just your algebraic shorthand. They taught this to not electrical engineers, but to electricians. Because, you know, if you're doing a trade, you may not necessarily feel comfortable with math, but most people feel extremely comfortable with this. I mean, you have the time, take a nap. All right, so I think that should be it for today. We've already been running for an hour. So tomorrow, bring these, any resistors you have, and if you have a multimeter, I have 3 different types to show you guys, depending on which one you have, so we can figure out the correct settings. And I'm going to try to teach you guys how to do breadboard. I may release a video beforehand so that you can watch it, and then this will be like the troubleshooting video. Will these lives be an everyday thing? I don't know. Do we need them to be an everyday thing? I can make them at least a most days thing. I'm, you know, having time to. I am going to show the dog. I am. Do we want the lives to be an everyday thing? Because then we could just set a time like that class starts every day and you can show up or not show up. Okay, I'll go get the dog. Type in the comments if you want these to be an everyday thing or not. Once every 2 or 3 days. Yes, most day thing. Okay, so maybe we'll do like 4 days a week and take Fridays off. Have a 3-day weekend. Nothing better to do. Okay, so we'll do that. And again, you don't have to show up. I'm not like recording attendance at all. These are completely optional. What do the light bulbs look like? Light bulbs look like Christmas lights. Every day for at least 3 hours. Yeah, that's not happening. And I'm actually probably going to set up, because I know some of you guys are like, well, I want to actually talk to you and ask you questions more in person. Probably what I'm going to start setting up towards the end of this week for next week is like remedial. Like I'll put you guys in like a group of 6 and do a video chat, because trying to video chat with 30 people is not going to happen. It's not. You guys can't even like keep a comment section like short. So we're not going to do that. So probably going to put you guys into like groups of manageable. I'll probably be using Google Hangouts because that's what I have. Skype, I find extremely glitchy. I don't enjoy it. So I'm probably going to use Google Hangouts. Also, you guys all have Gmail addresses. Otherwise, you wouldn't be signed up for the classroom. So no, 30 people aren't going to show up, but 23 showed up to this. So oh, Jocelyn, you don't understand. I actually put an hour of makeup because I saw my face in the camera. I'm like, oh, I look dead. I'm not sick, but I apparently look sick on camera, so I put makeup on today. Okay, I'm going to go grab the dog. I'll grab the older one first. Diana, Dee, come here, girls. Yeah. I'll pick them up because they're actually. Oh, maybe the younger one first. Oh no, Dee Dee, come here, come here. Good girl. Come here, fat girl. Okay, so this is Diana. She's 60 pounds. She's actually a little fat right now. She's 62 pounds. We've been feeding her too much. So she's a retired racer, so you can see her ribs, but she's still fat. Greyhounds always look underweight, even when they're overweight. She's strangely calm when I pick her up. Don't really know why. So yeah, she's a greyhound. Yeah, she's big. Juniper, you know she doesn't like that. Come here. And so that's Diana. This is Juniper. She's new. This is her 3rd week here. Yes, Diana, I know. Come here, honey. And so they look actually similar, which was not planned. That was just by random chance. So this is Juniper. Notice no gray on the face. And so she is actually a little underweight because we just got her. So we're fattening her up. To help the dog the dog will definitely win. The faster males go about 45 miles per hour. The females go about 35. Usain Bolt, I think, goes like 15. So I do not have a cat. Diana hates cats. By that I mean she'll eat them. So no, I don't have the complete rat cat dog chain. They do kind of look like twins. Diana is actually 6. She just turned 6 in December, and Juniper will be 3 in May 5th, I believe. So, yep, that's the 2 dogs. Juniper has some separation anxiety. She kind of cries whenever I leave the room. So actually, she's been in the room a lot of the time, just not on camera. They gonna have babies? No, they're both girls, so definitely not. Get a Doberman. No, I think I have enough dogs. I don't like to be outnumbered. Diana's the older dog. Juniper is the younger dog. No, then they're both spayed. I'm very for adopting already existing dogs. I've never owned a puppy and probably never will. They're a ton of work. Get a guinea pig, maybe. Diana from League. No, she's actually named after Diana Prince, Wonder Woman. And Juniper is named after Juno, the Greek. So they're both named after Greek goddesses or Roman goddesses, depending how you look at it. You're going to be late to get your breakfast? Okay. Favorite anime? Right now? I'm actually not currently watching it right now. My husband's upstairs watching Hunter x Hunter for the 2nd time, so we enjoy that, but I don't know if I have a favorite. So this is turning into an AMA, so I'm going to sign out. Okay. You guys are welcome to send me private messages on any of the assignments. Feel free to send me reminds. No, they're both neutered. It's over. They lost it, Joseph. It's gone. Bring him on the left. That would be like the thing he would least want to do. He absolutely is avoiding this room right now. So we'll see. I don't know. Maybe he'll get more used to it as time goes on and we get stir crazy being stuck in here together. So again, last things last, make sure you do the problem set. I know Alex has already done it and I've looked at it and it looks good so far. I got to get out the rubric. And so that please do that by Friday so I can get a good update on where are we with waves so we can kind of finish that out. Same thing with the lab. Cindy's already done it and it looked really good, just like a tiny minor mistake, not a big deal. So please do that. That lets me know if we understand it. If you did receive help on it, please let me know because that'll let me know where we're still having trouble doing it ourselves. So it's fine if you ask for help. Just do let me know that so I know like an accurate understanding of where we're at. Are you gonna save this live? I intend to and then post it. Um, I think that's what naturally happens. We'll see though. I'm trying this for the first time. I actually do have a like video recording of me doing most of this like on like the whiteboard talks. Um, so again, we'll see what happens. So again, make sure you're doing your labs. I'm going to be assigning a circuits lab. Well, these circuits labs I'm going to show you how to do tomorrow, and then after that, I'll probably be assigning circuits labs again on Pivot Interactives. So hopefully that's working. How many points have I lost? I don't know. I didn't grade it. It actually looked pretty good, like, especially your velocity time graph, I thought was good because I can do that one in my head. The other one I actually have to sketch out before I can determine, but that's extremely close to what it should be. So you should be getting most of your points on that, Alex. Something due today. Yeah, so Char Lovely, we're starting the SDLs tomorrow. I'll probably have more video of me doing stuff like the hands and showing you guys how to wire. Is there something else due? I don't think there's something officially due today. I'm gonna probably just assign you guys things throughout the week and then be like, get it done by Friday, and then I'll have the weekend to grade and then Monday to start doing things again. Maybe I'll have things due Friday night or Thursday night so I can grade Friday, plan for next Monday, and not do a live. I'm gonna be pretty like loose on the due dates. Just please do them as soon as possible because it provides really good feedback for me. Because I don't normally, without you doing the things, I already know how we are because I talk to you in class. I see you in class, and that's obviously not going to work now. I do, but I'm not gonna play with you guys. So as far as I don't have a Discord. I haven't PC gamed in a while, but I guess it's about time to pull it out. I've mostly been playing on my Switch. What about the Pivot? The Pivot Interactives, so it's on the stream. I'll make an assignment for it today in the assignments section, or the classwork section. The Pivot Interactives is just a direct video measurement system, which is basically a way for you guys to do labs without having the materials or having to set it up yourself. It's they have the whole setup, they have all the information you need, but you need to figure out, well, how am I going to take information from this and solve the lab prompts? Can you put grades in at home? Yes, I'm putting in grades right now at the moment. Some of you may have noticed I think I've put in all the test corrections. If your test corrections are not up to date, please let me know. Am I going to grade that? Yes, I'm going to grade that. I have both a student account and a teacher account because I'm going to go through it as a student every time I assign them to you and then go through it and grade based on that. So yes, I am going to grade it. Am I going to grade it right now? I've graded a couple just to see how they got. By couple, I mean Cindy's. I don't think anyone else turned it in yet, at least as of yesterday. I think that's about it. So mostly we're going to focus on whatever labs we can do at home, video notes, and then problem sets. So still pretty similar to class. But yeah, I think that's about it. Hopefully you guys are at least taking the chance to relax as you should. Like it's kind of a stressful situation. Okay, I turned it in. Okay, I'll go check Jan. Last time I checked, it said you had interacted with it, but I didn't see any answers on it. No, I have not played Breath of the Wild yet. Me and my friend, we switch off games, and she bought it, and she has it, and she still hasn't finished it and gave it to me. So I'm going to be giving her 3 houses, although I might keep it because I have the time and buy the DLC for Fire Emblem 3 houses. When are the flashcards due? So when are the flashcards due? So I'm not going to have you turn in flashcards because that seems ridiculous and makes no sense at the moment. Probably what's going to happen is sometime within the next week or 2, because we have the time. I don't have Mario. Okay, we have the time, Char Lovely. So I'm probably going to do some sort of quiz. I don't know. But seriously be practicing them just because you do want to know this basic information. And then hopefully this covered any of the electricity stuff. You're like, I have no idea what that means. And I will be working on posting them. I don't actually have a physical copy because I forgot to bring one back, which was dumb of me. So I don't have a physical copy to write on, so I'm figuring out how to like do a nice written version online without making it look like crap. A quiz on Kahoot. I don't know. We'll see. I haven't been fond of Kahoot. I don't like the format. Um, so I'm still trying to figure out what format will be best for that. I mean, Simon, you're not even in class, but sure. Do we send a week? Yes. So please do send in your weekly video notes so that's easy to do online. Just take a picture of them and I'll just look at them. Well, then it's going to live in my class, Eduardo, because I can't get in there. You can't get in there. And my plants are going to die in there and it's okay. Um, yeah. Anyway, I'll see you guys. Feel free to contact me, but I am ending it. Have a good day. Do your work. Good luck. Stay safe. And I'll be sending out more information later today.